This video is on particle physics. This video was a request, hence why it's on physics rather than maths. So, atoms, the building blocks of the universe. Except that's not really true, because there are smaller, more fundamental particles known as hadrons and leptons, and that is what I'm going to be focusing this video on. So let's talk about hadrons first. These are what give the Large Hadron Collider its name, as it collides these together at high speeds to learn more about them. There are two types of hadrons, baryons and mesons. Baryons include neutrons and protons, which make up atoms. But baryons are not themselves fundamental. They are made up of particles called quarks. These quarks have different types, the main ones being up and down. The difference between them is that up quarks have a charge of plus 2/3, and down quarks have a charge of minus 1/3. This means that baryons consist of 3 quarks, so they always have an integer or whole number charge. This is also why protons and neutrons have the charge that they do. Protons consist of 2 up quarks and a down quark, while neutrons consist of 2 down quarks and 1 up quark. This means we can also have 3 up quarks, a delta plus plus, and 3 down quarks, a delta minus. Delta particles are actually more complicated than that, but we only need to know about delta plus plus. The other type of hadrons are mesons. These are made up of a quark-antiquark pair. Antiquarks are a type of antimatter, and as such are called antiparticles. They have the opposite charge to their corresponding quark, so anti-up quarks have minus 2/3 charge, and anti-down quarks have plus 1/3 charge. The main mesons that you need to know are pions, as these are mesons made with ups, downs, anti-ups, and anti-downs. Pions are given a designation based on their charge, so a pi minus is a down anti-up, a pi plus is an up anti-down, and a pi zero can either be an up or a down paired with its antiparticle. There are actually more different types of quarks, which are heavier than ups and downs, but still have the same charges. These are charms and strangers, and tops and bottoms. There's actually a few features about strange particles that you may be asked questions on. Strange quarks are involved in kaons, which are a type of meson, and each hadron has a strangeness quality, which dictates how many strange quarks are in it. Importantly though, strange quarks have a strangeness of -1, while anti-strange quarks have a strangeness of +1. Think of it like how down quarks and, by extension, strange quarks have a charge of -1/3. Similar to strangeness are up quark number and down quark number, which will become important later. First though, let's cover the other type of particle, the lepton, which is the type of particle that electrons are. Electrons have their own antiparticle, which is called a positron, which is designated by E+, which has a charge of +1. So, if you see E+, don't get confused. It's essentially the opposite to electrons. But just like how we have both up and down quarks, electrons have their own counterpart, which is called the electron neutrino, which has no charge. It is neutral. And the electron neutrino also has its own antiparticle, which is called the electron antineutrino, but it's also called the anti-electron neutrino, but it will never be called the positron neutrino. The anti can go before the electron or before the neutrino. It doesn't actually matter. And just like how there were different types of quarks that were heavier than ups and downs, we have different types of leptons that are heavier than positrons. These are muons and muon neutrinos, and tauons and tauon neutrinos. So, if neutrinos and antineutrinos have no charge, what's the difference between them? Well, we can explain it by assigning each a lepton number. As a neutrino is a lepton, it has a lepton number of 1, and an antineutrino has a lepton number of -1, as it's an anti-lepton. So, when these collide, you end up with a lepton number of 0, and both particles are annihilated. Similar rules apply to electrons and positrons, but you need to remember that an electron will have a positive lepton number, while positrons will have a negative lepton number, as they are the antiparticle. We can use this to determine unknown particles in interactions, as the lepton number is conserved. We can also use other numbers and their conservation to help us narrow it down. Up quark number and down quark number are pretty self-explanatory, but remember that an anti-up will have an up quark number of -1, and an anti-down will have a down quark number of -1. An anti-up is not a down, and an anti-down is not an up. The other number that we use is charge, so remember the charge of each particle. So, what kind of interactions are there? There are three types of interactions: strong, weak, and electromagnetic, EM for short. You'll often be asked to determine which type of interaction a given interaction is, so here are some tips to help. EM interactions are the easiest to identify. They always produce EM waves, hence the name, which will be represented by a gamma symbol. This is the type of interaction that annihilation falls under, so when an electron collides with a positron, they will annihilate and produce photons. So try to memorize your antiparticles. Weak interactions will produce a neutrino and a flavor change. A flavor change is when a quark changes type, so an up quark to a down quark, or the other way around. Also, see if there is a neutrino in the output, but not in the input. Strong interactions have no flavor change, so count the number of up quarks and down quarks on each side, and if it's a strong interaction, they will be the same. There's another better way of handling it though. Strong interactions don't involve leptons at all, as leptons don't experience the strong force, only hadrons and quarks. One last thing before the video ends. You may be told that for a specific interaction to take place, the particles will have to be headed together at high speeds. This will be because they will have the same charge, so they'll be repelling each other like charges do. So they need to be headed together very quickly to overcome the repulsion. And that covers pretty much everything you need to know about particle physics. Most questions will ask you to identify features of particles, such as their quark makeup or their charge, or give you an equation and ask you to tell them what type of interaction it is. So make sure to revise that.